My talk is about categorial dependency grammars that we use here in Nantes and also in Rennes with my colleague, by my colleague Annie Forêt. So categorial dependency grammars are a family of grammar that were introduced by Alexander Dikovsky and Michael Dektia in 2006. And well, we use them in Nantes, at Nantes University, and also in the University of Rennes, to modelize the syntax of natural languages like French or English, but also to modelize less common languages like Breton. Breton is a regional language in the west of France, which is one of the Celtic languages in this part of Europe. For this kind of languages, in fact, we don't have a lot of resources. So we try to modelize, in fact, those kind of languages using formal grammars rather than a big corpora or something like that, and something based on machine learning, because we don't have enough resources in a sense to modelize this kind of languages. And for that, we use the categorial dependency grammar, which are based on the notion of dependency, and use a kind of grammar based on categories. That is, we want to put the syntactic properties of the word on types, directly on types of the words in the lexicon. But in fact, when we look at the properties of this family of grammar, we see that there is a problem with one of the operator of the abstract family of language concept. It corresponds to the clean plus operator. It seems that it is an open question for categorical dependency grammar to know if this operator is inside this family of language. So in fact, it's a problem that is for us relatively important because we don't have a general constriction on grammar to have something that corresponds, for instance, to list of complement. If we have something that modelize one element, one part of speech, it's difficult to have the modelization of a list of this part of speech, for instance. So it's something that is important for us. In general, it's a good idea to have something that corresponds to list of elements. The same thing comes also from the fact that when we have the modelization of just a sentence, it's difficult to modelize a list of sentences. That's the kind of thing that we don't have naturally, in a sense, using categorical dependency grammar. So we want to resolve those problems. And our solution with Annie Forêt is to add a new symbol in the categorical dependency grammar, which are called barriers. So the plan of my talk, first I want to show you what is an abstract family of languages on the link with the CDG, the categorical dependency grammar. Then some introduction on category CDG languages. I want to show you the problem with the product, and finally, in point 4, our solutions for the product and also for the clean plus operator. After that, I want to conclude. So in this work, we modelize the language using a very simple idea. It's just finally the set of correct sentences. Well, it's the first thing that we can think about what is a language. And naturally, when we want to do this modelization, we try to find something like a grammar to understand what's the definition of this language. So there is a correspondence between a formal grammar, like G1, and a language using something like a parser or something that generates from this grammar the sentences or correct sentences for this language. Now, because we don't have just one grammar, we have a family of grammars. It corresponds for this concept, of course, a family of languages. So for a grammar, we have just one language, but for a family of grammar, we have, of course, a lot of languages, and all those languages create a family of languages. A well-known family of languages exists, as you can see on this slide. For instance, we can talk about regular languages, that is, the languages made from regular expression. Of course, it corresponds from the grammar to the notion of right linear grammars. For context-free languages that are used in computer science, of course, we have context-free grammars. For CDG, we have CDG languages. For recursively enumerable languages, we have something that corresponds to the unrestricted grammars. Now, when we have a family of languages, it's important to know the properties of this family. And we have particularly certain operations like union, concatenation, and this clean plus operation. We have also some properties linked with homomorphism and also with the intersection. So the different properties that correspond to this notion of abstract family of languages is linked to this different operation, the union, the concatenation, the clean plus, epsilon free homomorphism, inverse homomorphism, and the intersection with any regular languages. For instance, the regular languages define an abstract family of language. You can see it on some example. The union is relatively simple because if we have the first regular expression and the second regular expression, we can modelize the union of these two languages. Uses just this bar as the union operator. For the concatenation, it's the same thing. It's very easy. We just have to concatenate the regular expression. For the clean plus, it's also very easy because it's also very easy because we have this plus operator, and this plus operator corresponds exactly to the clean plus on languages. Finally, we have also properties on function on homomorphism, but well, it's not very important for me here. What we want to do with categorical dependency grammar is to modelize the clean plus. In particular, it is an open question for clean plus. We don't know if the clean plus is an internal operation for this family of languages. And there is also a problem with the concatenation. Our solution here is for us relatively important because we want to modelize a list of complex complement, for instance, or we want to define the conjunction of complex part of speech for the concatenation. The solution is these barriers that are introduced in categorical dependency grammars, and the solution gives us the fact that our family of languages are close under the clean plus, and also define an abstract family of languages. Our solution also resolves the problem with the concatenation. So now what are the categorical dependency grammar languages? In fact, they are based on dependency syntax. We modelize the syntax of a sentence using dependency. A dependency link together two words. One of the words is the governor, and the other is the subordinate. in the category, in a categorical grammar, that it corresponds to valencies on type associated to word. We have a positive valency for the governor and a negative valency for the subordinate. Now we have in this kind of framework, in fact, two kinds of dependency. We have projective dependency that are shown using plain arrows, and we have also non-projective dependency, which are presented using a dash arrow. Here, in this example, we have one non-projective dependency between more and than, and the other one are projective dependencies. For projective dependencies, the modelization is in types associated to the type of the governor or the type of the subordinate. In the type of the governor, we have a positive valency D on the square brackets, and on the subordinate type, we have also D, but in the head of this type, in the square bracket. For the non-projective dependencies, in fact, we have potential, which are the exponents in the types. And these exponents create, using polarized valencies, all the non-projective dependencies. Here is an example of a sentence with only projective dependencies, but also we have non-projective dependencies. For those non-projective dependencies, we have potential that are type expressed using polarized valency. They are oriented on the left or on the right. On the governor, we have a positive valency like this one, like the arrow on the top east, D. And for the subordinate type potential, we have a negative valency on the southeast. Here is the complete example for our example. This deal brought more problem than profit. As you can see, a lot of dependency are projective and correspond to the square bracket, and the non-projective dependency correspond to the red valencies, conj, in more or in than. The calculus corresponds to two parts. One is the part that corresponds to projective dependencies. We have a simple elimination rule as a categorical grammar, as in categorical grammar. We have also the case where we have an empty head. Well, it's not something very important, but it is sometimes needed. We also have something that can iterate a projective dependency. If we have a word with several complements, it's possible to use this construction where we have a C star. It means that this word can have several complements. Finally, there is a part that corresponds to the non-projective dependency, and it corresponds to the potential part of the type. Here we have at this time to seek dual polarized valency like C on the left, the northwest C on the southwest C must be in the same concatenation of the polarities, and there is a condition that is the P there must not have those two dual valencies. Is the first available principle. The link between the calculus and the dependency structure is as follows. From the lexicon, we have types. Types can create derivation using the calculus, and using this derivation, we can find the dependency structure. For instance, for this sentence, John ran fast yesterday. We find that we have three dependencies, and the main word is ran. that correspond to the axiom S. Here's an example of a non-context-free language, which is mixed of N, A, B, and C. We have a mix of those 3 letters. We have the same number of A, B, and C. And the grammar that corresponds to this this language is on the left of this slide. We have 8 types for A, 2 types for B, and 1 type for C. Now, how can we build the product of 2 categorical dependency grammar languages, classical CDG? I do it on an example. Here is an example of the language EN, BN, CN, where N is an positive integer. This language can be modelized using the CDG on the left. As you can see, we have 2 types for each symbol, and in the derivation or in the structure that correspond to this to an example of this language, like A, B, 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 C, C, C. We have 2 parts. The first part corresponds to the list of A, linked using projective dependencies. On the left, we have something that corresponds to a list of B and C with the same number of B and C, linked using 2 kinds of projective dependencies, C and B. There is a correspondence between the C and the E using a non-projective dependency D. Each C is linked to one of the A, and the final result is that we have exactly the same number of A and the same number of C. Because we have the same number of B, the total is that we have the same number of A, the same number of B, and the same number of C. The complexity of this grammar is ON4. If we want to create the product of this language with itself, the first idea is just to introduce a second axiom, in a sense, S2, and add a new type to B that corresponds to this new type for S2. But in fact, it's not the good idea. It's an unsuccessful attempt because we have some string that does not correspond. We have a string that does not correspond to the product of this language with itself. For instance, we have the string AABC, ABBCC. You can see that it does not correspond to EN, BN, CN with itself, the product of this language with itself. And the reason is that we have the possibility to link the last C with the first A using a non-projective dependency D, using this grammar here. So this grammar is not the proper one for the product. What we need, in fact, is to duplicate the initial grammar, the grammar for EN, BN, CN. The first one is with 1, and the second one with the index 2. And we just link the first grammar with the second grammar using a projective dependency S2. Of course, it works. That is, we have exactly the product of EN, BN, CN with itself, but the problem is that we have now 2 names for non-projective dependency, the name D1 and D2, and the consequence is as we have a higher parsing time complexity, that is ON5 rather than ON4. So now our solution for this problem and the problem of the clean plus operation is the introduction of barrier on CDG. The solution is relatively small. In fact, we just add a new symbol in potential. This symbol is a barrier. So now potential contain the polarized valency, but also can contain this barrier. The first available rule is different from the first definition for the CDG. That is, when we want to have a positive valency corresponding to a negative valency, we must verify that between them there are no barriers. And the consequence is that what we have is something that can forbid non-projective dependency between two parts. For instance, here we have the simple modelization of the product of AN, BN, CN, and it works because we add a GIS barrier on the first type of A, and this barrier inhibits the fact that we can have a dependency between the last or the rightmost C and the leftmost A. So now what we have is exactly the product of EN, BN, CN using this very simple mechanism. And the consequence is that what we have is a categorical grammar with barrier with only one non-projective dependency name. So the passing time complexity is the same as what we have for EN, BN, CN. With this barrier, we also resolve the problem with the clean plus of EN, BN, CN, because what we want to do is the list of element of EN, BN, CN. Here, for instance, we have the case with where we have three elements in this set EN, BN, CN. The first one is ABC. The second one is AA, BB, CC, and the third one is ABC. As you can see, in fact, this barrier on the first type of A inhibits the fact that we can have non-projective dependency between the different parts of our solution, and it gives a direct solution to the clean plus operator for this grammar. Of course, it is a general result. That is, it is possible to grammar to have this clean plus for this grammar. Second consequence is that we only need just one non-projective dependency name for this clean plus operator. And so we have the same passing time complexity for this grammar, the clean plus of EN, BN, CN, and for EN, BN, CN. The general construction for CDG with barrier is more complex than what I show you here. In fact, we have three first steps that are important if you want to apply this principle. Firstly, we just inhibit the fact that we need, we don't want anti-heads in the lexicon. So it's possible to transform any grammar using a grammar without anti-head. The same thing is for the point number 2, where we don't want that S, the axiom, can be used as a governor. It must only appear as the main type for the main word in the sentence. The step 3 is more important in the sense that we want to know which type can occur as the leftmost, occur only as the type of the leftmost token in any derivation, and the other types that can only appear on one token which is not the leftmost. That is the most complex transformation there, to have something that corresponds to exactly to this principle. After that, we just have to add a barrier on the leftmost type that are identified by the step 3, and we just create a loop with the axiom using S under S. The final solution corresponds exactly to the clean plus of the initial grammar, and it has the same parsing complexity. So a final conclusion on open question on this result. Firstly, for us, it is relatively important to modelize the product and the clean plus of natural languages, because sometimes it is useful to modelize the conjunction of part of speech, or list of complex complement, or list of sentences, for instance. So for us, it's relatively important. Our proposal allows such construction for categorical dependency grammar with barriers. And this construction has no penalty for the product, but also for the clean plus. Finally, the final result, in a sense, is that what we have defined define an abstract family of languages, which is a nice result in a sense. But of course, there are also open questions in this framework. First, we don't know if classical categorical dependency grammar is or not an abstract family of grammar. We don't know the solution for this family of grammar. And the second question that we have for the moment is how can we also develop some learning algorithm for this barrier? For the moment, we have an algorithm for just the CDG on when we have a corpora and we want to define a grammar from this corpora. So it's possible for using this learning algorithm. For the moment, we don't know how to introduce barrier on this sample mechanism to have something more complex than what we have with categorical dependency grammar. Okay, thank you very much for your attention.